Welcome to Surely Physics episode on simple and physical pendulum. We're going to be looking into the angular frequency and the period of simple and physical pendulums. So just to get you started on a couple of types of pendulums, this first one is called a simple pendulum because it's a mass at the end of a lightweight cord or string, where the mass of that is mostly concentrated on the end of that swinging object. So a pendulum is just an object that swings back and forth, generally under the influence of gravity as the only force that's causing that back and forth motion. Where a physical pendulum is more like the one you see here. It's not just a mass at the very end, but there's a body to the makeup of that pendulum. It's not just a very small cord. So if you've ever looked at a grandfather clock with the pendulum that swings back and forth, it's got a large, thick trunk that goes down. It's not just a single mass at the end. So that's just our difference between physical and simple pendula, and they're treated exactly the same way, the way we're going to solve for them. They just have a bit different solution in the end when you look at the properties that make them up. All right, so the way we're going to do this is approach it from simple harmonic motion standpoint. And just a couple of things to remember, just to bring back to this from our last lesson. When there's simple harmonic motion, the displacement function of any simple harmonic oscillator is given by x of t as a function of the amplitude times a sine or cosine of omega t, where the omega is the angular frequency of the there we go, of that oscillating object, angular frequency. And if you take the derivative of this, you get the velocity of that object at any point. And that's going to be a negative a omega sine omega t. And the acceleration, negative a omega squared. And we're back to the cosine. We take the derivative of sine, we get a positive cosine omega t. And this omega is just coming from the chain rule right in here when you take the derivative. All right, so there's just some tools we'll need to unpack. And one other thing is I introduced that mass spring system. And the way we solve for this one is just by first looking at a force diagram. If we pull the mass to the side, there's a force from the spring, kx, going to the left. Now this is the positive direction. Our next step would be to apply the Newton's second law, F equals ma. And we'd have a negative kx here equal ma. And this is where we bring in the x in the a functions. Substitute x in right here for the x and a over here. And out of that we got the angular frequency for this system. And I always forget if it's k over m or m over k. The stronger the spring, the faster that back and forth frequency, so that's going to go in the numerator. And the greater the mass, the slower the frequency, so that's going to go in the denominator. So that's what we got from the mass spring system. We invert omega multiplied by 2 pi to get the period is root m over k, where k is that spring constant. Okay, so that's just to sum up the mass spring system. And the reason I'm doing this with, before I present pendulums is because the method we're going to use to solve pendulums is almost exactly the same as this one. That's for the mass spring system there. And the omega and the t, they're going to be found very similarly. Now the main difference though is this mass spring system is moving in a translational kind of way, where the pendulum is rotating about a point. So it's going to be easier to apply this with rotational motion instead of translational motion. We're going to be using some of the torques equals I alpha instead of F equals ma. But our process is still the same. We're just going to convert all this to the rotational analog first, and we'll be able to solve. All right, our first scenario I'm going to look at is a simple pendulum. And it's going to be solved up to a certain point in exactly the same way as the physical pendulum, where we have instead of a point mass, we've got a mass distributed throughout that pendulum shape. So let's start with this simple pendulum. We have a a point mass out here. We'll call it M. And there is one thing that I'm going to talk about briefly right now, but we're going to have it's going to come back toward the end of this problem. It's really important to note that the way I'm going to solve this is for angles that are very small. Okay, these are small angles. It's not an angle. Okay, it's an angle. There we go. And generally talking about like, less than 10 degrees or so. Okay, a very small angle. Now we will be working with radians, but I think just somehow 10 degrees is a little easier to think about in your brain instead of the equivalent radian value. So less than 10 degrees or so. And I'm going to talk more about that later. If you do start a pendulum up at a really high angle, then this approximation I'm going to use doesn't work quite well. But essentially what we want is a very small back and forth motion such that it's not really lifting up a whole lot. Okay, it's just kind of, in essence, just sliding side to side just a little bit. It's more of a side to side motion of the pendulum rather than a big old swing. And besides, with most pendula, you might realize once you get them started, they'll swing for quite a bit of time, but the angle does reduce after a bit without any extra energy added. It'll swing back and forth for quite a bit at those small angles without stopping. Whereas if you pull it up to a really high height and let it go, it quickly reduces down to sort of one of those small angles anyway. So pendula do tend, because there's less drag when they're not moving as fast, they tend to swing for a much longer period of time at those small angles anyway. And that's usually how pendulums are used and work. They're very helpful for keeping time and other things like that. They have been used like that for centuries. Okay, so here we go. What we're going to do is try to find the angular frequency and the period of this swinging simple pendulum. Period is very helpful. If we can get it to swing back and forth in 1 second or a multiple of that, like 2 seconds, then you've got a timing device. So what properties are going to give us the time for this pendulum? Can we turn any old mass hanging from any old string into a timing device? That's a very useful thing. All right, so just like the mass on the spring, what we're going to do is draw a force diagram and apply Newton's second law and see how we can come up with an omega and a period from that, a t for the period. Here we go. We got a force diagram. There's going to be a tension in that string, and there's also going to be a weight. And I'm going to go ahead and mark this is theta right there. All right. So one other thing that might be helpful here, it's going to be needed in the end, is going to be a length. So we're going to call the length of this tension line L, lowercase l there. That's just one other little piece that's going to be needed. Look at the mass and the length, and here we go. Now, when this pendulum, when this mass starts to move, it does have a circular kind of a motion. If we pull it to the side and release it, it has a circular motion. So what I'm going to do first is call this theta an initial theta. All right, that's going to be the starting point, and we're going to use an initial small angle for our angle there. Okay, and then it's going to rotate this way. Now it's going to rotate from gravity, but take note here: gravity does not pull perpendicular to that swinging radius there. Right, it pulls downward always. Even when the mass is here, gravity is pulling downward. So as you can see, the angle between that weight and the chord is going to change. When the chord's here, the angle is going to be greater. When the chord is down at the bottom and the mass is at the bottom, then the angle between weight and the chord is 180 degrees. And likewise, it's going to change as the mass swings to the other side. So this is going to be, weight is always pulling straight down, and the angle between the chord and that weight is always going to be changing. So we are talking about rotational motion, and while you can solve this one with translational motion, if you think about like the x direction displacement of the mass or the y direction displacement, you can solve this problem like that. I think if we go right to our rotational mechanics, it works just as well, and I think with a little less hand waving and fudging. So how I'm going to approach this one is with torque. Instead of summing the forces and doing a, using the force diagram, I'm going to use a torque diagram and consider this as torque. So let's consider the sum of all the torques acting on this object, causing that mass to have an angular acceleration instead of a translational acceleration. All right, there are two forces involved. We got the tension from the string and we got the weight. Now the tension is applied at the mass itself. There is no torque arm. Let's revisit torque. Torque equals R cross F, and which is the torque arm times the force times the sine of the angle between them. Since the tension is applied at the mass, it's not applied off of it, okay? So the tension is applied at this mass. It's not at any torque arm. There's zero torque arm. It's the one pulling in. So it's also 180 degrees between, if you're considering like, oh, is the length of the string the torque arm? You could also consider that, but it's at 180 degrees, so sine of 180 degrees is also 0. Therefore, the torque from the tension is 0. And all we're left with is the torque from this weight. The weight is applied out here on the mass, and it's at a torque arm of the length of the string away. So if we apply that, the torque due to the weight, torque due to gravity, would be R. In this case, it's the length of the string, distance to the mass, times F, which is mg, and sine of the angle between them. Now, if you look at my angle here, that's the initial angle, but that angle would also correspond to this one down here. So that angle between R, this purple line here, is the vector. I'll call it R hat, okay, for the direction of R. That's the direction of R. The distance of the length of R is L, and the force is always going to be at an angle theta, even when the mass is down here or down here. That angle theta is always going to be the designated one. So I'm going to leave this as an L mg sine theta is the torque due to gravity. Okay, if I call this the positive rotational direction, and what direction is the torque due to gravity? It's in the negative direction. So therefore our torque is going to be R F sine theta, but in the negative direction. Now I'm going to leave the I for the simple pendulum as just I for now, because in just a moment we're going to see where it diverges, where the physical pendulum diverges from the simple pendulum. And we're just going to leave that I in there because that's what's going to make them diverge. It's going to make them separate and different. So I'll just leave this as I for now. And then we got alpha. Okay, so here's our Newton's second law application to the scenario. The torque is negative LmG sine theta and equals I alpha. All right, are we kind of stuck? Yeah, for a couple reasons. Now first, let's consider what the mass on the spring look like. This is the step we're on right now. We've applied Newton's second law and we have an expression. Now what did this look like? This had an x and an a displacement and an acceleration. What have we got now? We've got a theta. We've got an angular displacement from the rest position. And we have an angular acceleration. But what's the big difference here? There's a really ugly looking sine function in here. Notice we didn't have that over here. This wasn't like a sine of x, in other words. This is just x. So what the heck do we do with that? Can we solve this? Well, in order to solve this one, we will need to unpack angular displacement, angular velocity, and angular acceleration. So we can substitute in for these characters here. But we don't want a sine of a cosine. And what I mean here is if displacement is a cosine omega t, then angular displacement is going to look very similar. It's going to be some kind of amplitude cosine of some kind of angular frequency times time. Now if we plug this in for theta, we'd end up with a sine of a cosine omega t. What the heck is that? That's not going to be like, stuff's not going to be canceling out there. What I'm going to do first is bring this out. I'm going to make this clear. If instead of an x function, what will that theta function, that angular displacement, look like? Well, it'll have the same format, but I'm gonna just change a couple of these characters around here in a moment. So what we're going to be doing next is we're going to find the angular velocity in order to figure out the angular acceleration function, see what those are going to look like in the rotational form. And when we find angular velocity, we're going to have a couple of confused characters here. You see, this omega is from the rate of change in angular position. Okay? This omega here is not the omega over here. This one is dealing with the frequency at which this pendulum swings back and forth. Okay, we're talking about like in our Simpsons situation here. We're looking for that frequency. How often does it make a back and forth motion? That's what this omega is about. So I'm going to start calling it omega f. It's kind of redundant, but just for the case here, I want to differentiate it between the angular velocity of the actual rotational motion of the mass. That's different from the rate at which this thing is swinging back and forth. So for example, the speed of this mass moving at the bottom has little direct bearing on how often the mass will swing back and forth with a full motion. All right, so I'm just going to call this omega f. Talk about that's the frequency, not the angular velocity of the system at that point. And the other thing is, what is amplitude in this case? Well, I've kind of already defined it with a character here. We're going to give an initial angle, and that's going to be the maximum angular amplitude. So I'm just going to start by rewriting this. Theta is a function of time. Angular position is a function of time. Is equal to the initial angular position cosine of my little omega sub f t. That's just I'm choosing to use here. And now if we take note that at omega, the angular velocity of the system equals d theta dt, that means we're going to have an angular velocity as a function of time equal to, and we're going to have a initial theta, and the derivative of cosine omega cosine is negative sine. So we're going to have a negative sine omega ft. Then we have to use the chain rule, take the derivative of what's inside here to get another omega f. So let's clean that up. Our angular velocity as a function of time is negative. Amplitude, angular frequency, sine of omega t. Okay, and you see the importance now. This is a constant. This is a changing value as a function of time. And next, let's note that alpha equals d omega dt, the derivative of that omega function. So our alpha is a function of time. It's going to be equal to, we do this whole derivative, we'll get a negative, that's quite a negative sign. Negative remains, and this sign will turn into a positive cosine. We're going to keep the negative from before though, and through the chain rule we'll get another one of these angular frequencies. So omega frequency times omega times the angular frequency is omega squared. Cosine, back to the cosine. All right. Here's our new box of tools, from angular velocity, angular displacement, angular acceleration. That's what we've got for this new system, this new simple harmonic motion system. All right, so what can we do? Before, with the mass spring system, I plugged in x of t equals a cosine omega t, plugged it right in there, and plugged in a negative a omega squared cosine omega t, plugged it in for a, for the acceleration. That's where we're getting the square root out because of this little omega squared character is how we got the square root of k over m through that algebra of plugging those in. Now, if I start plugging like theta into this sine theta here, we're going to get something that's not very useful. We can't really solve it yet. So I want to talk about the sine theta next. Get my calculator out here. All right, there it is. And also make sure, go into mode, and you should find where you can change your mode from degrees to radians. Make sure you switch over to radians here if you want to try this out. We're going to go for some small angles. So my mode is in radians now. And first off, I mentioned small angles earlier. Now, if you look at 10 degrees, and we want to figure out, what radian amount does that correspond to? Well, if there are, 360 degrees in 2 pi radians. So if you go around the circle one time, that's 360 degrees, and that's equal to 2 pi radians. If I multiply 10 degrees by 2 pi radians, for some reason did exponent there, 2 pi divided by 360 degrees, there are 2 pi radians in 360 degrees. We're going to conversion factor here. That corresponds to about 0.174 radians. So 10 degrees is about 0.17 radians. So I'm going to keep that as an idea for a small angle radian amount. Now, if you plug in a small angle like that, and with the sine function, if you do sine of 0.17, that's sine of 10 degrees about. Look at the number that you get out of that. Sine of 0.17 is 0.1691. Is that just a coincidence? 0.169 rounds to 0.17. And if we go even smaller, let's say sine of 0.1. Sine of 0.1 is 0.09983. That rounds to 0.01. A lot better than 0.169 rounded to 0.17. All right, if we go even smaller, sine of 0.01, even smaller angle. Do you see how you're getting closer and closer and closer to the actual number? Now, if you go much higher than 0.17, if we do like sine of 0.34, that's twice 0.17, it'd be like 20 degrees. That's 0.334. It's still pretty close. Even 20 degrees is a good small angle. If we go much higher than that, let's try sine of a half, 0.479. You see how a half compared to 0.479, we're about, about 5% different there. So we're starting to get away from the value, the approximate value. What I'm trying to really talk about here is something called the small angle approximation. If you ever hear that word, using the small angle approximation, that's what this is referring to. It's the fact that with small angles, sine of theta is approximately equal to theta itself. If we go up to a high angle, let's say sine of pi halves. Okay, let's say 90 degrees. Pi over 2. Wow, that's 1. Now pi over 2, just to get an idea here, is 1.5. So sine of 1.57 is 1. That's a big difference. 1.57 and 1 are not completely different. They're close, but on an angle scale, they're very different angles, or they're very different numbers. And just as you get smaller and smaller from there, if I change that pi over 2 to pi over 4, and pi over 4 is itself 0.78. You see, as you get smaller and smaller angles, we get closer to this approximation. That sine of whatever number in radians you put in there is approximately equal to theta. So really, we could do 20 degrees or less and still have this small angle approximation. What does that do for us? Something really nice, mathematically speaking. turns this ugly expression with a sign into the slightly more wonderful expression without the sign. We approximate sine theta as just a theta. The little tag here, little thing stuck to your shirt says, by the way, you should wash this with small angles, okay? So only small angles work here for this approximation. But now, the beautiful, wonderful thing is this expression now more resembles negative kx equals ma. If we look at those two expressions side by side, negative kx equals ma, you've got an angular acceleration that corresponds to a translational acceleration. You've got an angular displacement that translates to or corresponds to a translational displacement, and this k over here is a constant, and LMG is a bunch of constants. I corresponds to m as a rotational analog. So all these forms fit. I think we're ready to work this through. All right, let's see what we can get out of this. Negative LMG, we're going to keep that. Here's our constants. Now if we substitute in theta as a function of time, we've got an amplitude, that initial angle that you set it has to be a small angle that you set the pendulum at, cosine of omega ft equals I times alpha. And alpha over here is a negative. Put a Q there for some reason. I'll move my little definition over a little bit. Get it out of the way. There we go. Go away, definition. We get a negative theta initial omega f squared cosine omega ft. Okay, it's a big old mess, but let's clean it up. If we divide both sides by cosine omega ft, those two cancel. If we divide both sides by the amplitude, that cancels. And that's all I think that cancels, so let's see what we've got left here. Ooh, there's a negative on this side and a negative on that side. Multiply both sides by -1, they cancel as well. We're left with an LMG on this side and an I omega f squared. So if we're to solve for that omega f, that omega for a pendulum, we would have the square root of L mg, that's the length, divided by I. In class, everybody out there, I'm on YouTube, I guess it'd be everybody out there. This is the angular frequency for a pendulum. And this is actually good for a physical pendulum, as we're going to see here in a moment, because we can leave the I here, whatever that I turns out to be. It could be for either a point mass, like for a simple pendulum, for a simple man there, or a physical pendulum. When you've got more than just a point mass at the end, you've got some kind of body that makes up not just the bottom of the pendulum, but the whole length of it. It could be a person on a swing like you see here. That's a physical pendulum. Kid swinging. All right. And since we've got omega being equal to 2 pi over the period, then period equals 2 pi over omega. So we can find the period for a physical pendulum. I'll call this PP for physical pendulum. It includes the I value. It'll be 2 pi times the inverse of this omega. Okay? And that'll be I over LMG. Now, how does this apply to a simple pendulum? I'm going to turn off my calculator there. We don't need that anymore. On a simple pendulum, what is the I value going to be? Well, we have a mass at the end of a string. Okay, so here's the M. And since this rotates out here, you might call this the R value. So R is equal to the length L. And we do have a point mass. So what is the moment of inertia of the point mass? We're going to go ahead and fill this in. What is the I value going to be? Filling it over here. for point mass, it's mr squared. In this context, that m is the length L. Now this is going to be the simple pendulum because we now have a defined I value. The angular frequency is therefore going to be L mg divided by the I value mL squared. There's a magical thing that happens here. This m cancels out. Mass doesn't matter. Now let's pause, reflect. Does that make sense? In a gravitational field, potential energy converts to kinetic energy, all that kind of thing as the pendulum goes down. But besides that, does mass affect the acceleration of an object under only the force of gravity? No. So if gravity is affecting it, remember that mass gives it a greater inertia, greater tendency to stay at rest, which requires more force to accelerate the object. So with a greater m, you do get more force to accelerate the object with a greater weight, but you also get more inertia. The overall effect is mass cancels out. Mass doesn't matter. Drop a brick and a feather in the absence of air resistance, and they'll both accelerate the same rate. So we should get a mass canceling out here. We also get one of those L's canceling, and while it looked like a greater length would increase the frequency, shouldn't it make sense that the longer length decreases the frequency? It takes longer to go back and forth. And likewise for the time period, shouldn't a longer length extend the time, not make it shorter? So with the period, the length should be up in the numerator, not in the denominator. And look what happens here. Because of when we consider the moment of inertia, oh yeah, it's m times length squared, m times r squared. And that'll bring that length character down here to the bottom. Overall, what's happening here is one of those lengths is canceling out. So we end up with, I'll rewrite this over here, the omega for a simple pendulum is the square root of g divided by L. And that's it. It's not dependent on that mass at all. And likewise, the period, because it's going to be the inverse of that times 2 pi root L over g. Do pendulum clocks made on Earth work on Mars or the Moon? They won't. The acceleration due to gravity of the planet is a major factor here. And let's see, the greater the g, the faster the motion. The lesser the g, the slower that back and forth frequency motion. The longer the L, the slower the frequency. The greater the L, the faster the frequency. And likewise for time. I think that makes more sense. We can make a period, a pendulum with a period of exactly 1 second with this. 1 second equals 2 pi root L over 9.8. We plug those in. How long does our pendulum need to be to have a back and forth motion of exactly 1 second? You could also make it 2 seconds, so it goes 1001, 1002, or you make a quick one, 1001, 1002, 1003, 1004. That's what we're going for here. What length should our pendulum be? So we got a 1 divided by 2 pi. You can't see this on my calculator right now, that's fine. And enter, we're going to square that. It's 0.02 something, it doesn't matter. And multiply by 9.8. 0.2482 meters. Make a pendulum that long, and you'll have a period of 1 second. As long as you use small angles. You need that small angle approximation. Okay, so there's our simple pendulum. Now, what about our physical pendulum? Okay, simple pendulum with a mass on the end of a string, and physical pendulum where there's, masses distributed throughout that pendulum. Well, in that case, we're just going to have to go back to this goober here. Period of a physical pendulum equals 2 pi root I over LMG. But the thing here is, be careful. As length increases, does that mean the period decreases? Because when length gets bigger, we're dividing by a bigger number. Does that mean the period decreases? No. Because remember, in here, embedded in here is the units kilograms meters squared. And there's a meters down here. So remember that meters in the bottom will cancel, and this I value actually has the length of that pendulum puts it up top. So don't forget about that if you're ever using this to figure out relationships between changing the length or the mass or the I value. Also remember there's a kilograms up top, and that's going to cancel out with the mass down below. So don't forget about that if you're ever comparing quantities. You know, will this affect the period in this way? Remember that I is loaded up with kilograms meters squared, and that'll cancel out the kilograms and one of the meters on the bottom. But anyhow, that's your simple and physical pendulum. Just do a quick rundown. See the big picture. It's fairly easy to solve these as long as you remember the equations of motion for simple harmonic oscillators, A cosine omega t. It's the only thing you remember for this. Okay, you apply that. Take the derivative twice for the acceleration. Apply F equals ma to a force diagram. There's always going to be a negative restoring force to the system, and that gives us a second order differential equation. Plug in the x, plug in the a, and you'll get your omegas out of that. That's how you solve them, whether it's a mass spring system or that pendulum system that we did today. Okay, and that's the end of this episode.